Hey, welcome back. In this video, we're going to talk more about Turan extremal functions. We've already discussed them for some families of graphs, and we've used various inequalities to prove bounds on them. So just to review, the extremal function ex of n comma h is defined as the maximum possible number of edges in an h-free graph of order n. We've already looked at how to find sharp bounds on this extremal function when the forbidden graph h is a complete graph and when it's a star. We found exact values for stars. And we also saw how to prove upper bounds on these Turan extremal functions when the forbidden graphs are complete bipartite graphs. For complete bipartite graphs, the Turan extremal functions are still open problems when both of the parts have size at least 4. In fact, even finding bounds that are sharp up to a constant factor is an open problem for complete bipartite graphs where both parts have size at least 4. And that is what this bullet says pretty much, although the bullet is less specific than that. And in this video, we're going to focus on trees, and that includes paths, that includes stars, and many other special families of trees, some of which we'll discuss. And we'll see in particular how to get sharp bounds on the Turan extremal functions of paths. Before we get to any trees, let's look at a few simple properties of Turan extremal functions. We will say that a graph G contains a graph H if some subgraph of G is isomorphic to H. And if we suppose that G contains H, then I claim that the Turan extremal function of G is at least the Turan extremal function of H. Why is this? Well, if we have a graph that avoids H, then it also has to avoid G. Otherwise, if that graph contained G, then in the copy of G, we would find a copy of H. So here's a problem for you to think about that's pretty similar to the last one. Suppose that G is obtained from H by adding a new vertex, and that new vertex is isolated, so it has no edges to the rest of H. Prove or disprove the following statement. For all such G and H, the Turan extremal function of n comma G is equal to the Turan extremal function of n comma H for all n sufficiently large. So starting out, we're going to prove a general upper bound on the Turan extremal functions of trees of order k plus 1. Just to recap what a tree is a connected graph that has no cycles. So we can say that it's a connected acyclic graph. For example, here's a tree. There's a star, that's a tree. A path, that's a tree. A triangle has a cycle, so that's not a tree. So we see the paths are trees, they don't have any cycles and they're connected. The stars our trees, stars K1K, are also complete bipartite graphs where one of the parts has size 1. And there's other families of trees that we can look at as well. So if you want to generalize the star, you can consider any trees that have a single vertex of degree at least 3. So if there's only a single vertex of degree at least 3, that means all of the other vertices have degree at most 2. So a graph that has a single vertex of degree at least 3, we can put that vertex of degree at least 3 in the center. We'll just call it the center. And the other vertices, we can just think of them as paths attached to the center. And we can call them legs. So these type of trees with a single vertex of degree at least 3 are known as spiders. Stars are a special class of spiders where all of the legs have length exactly 1. And spiders where all of the legs have equal length are known as balanced spiders. And we'll see spiders more later in the course. Here's another family of trees. These generalized paths, they are known as caterpillars. Caterpillars have a central path, and then every vertex in the caterpillar has distance at most 1 from the central path. So there's an example of a caterpillar. So in this video, we're going to prove a general upper bound on Ex of nt that holds for any tree T of order k plus 1. Our bound will be in terms of k and n. There is a conjecture of Erdős and Sós that the extremal function of n comma t is less than or equal to n times k minus 1 over 2 for every tree T of order k plus 1. This conjecture was recently proved for n sufficiently large. And it was known to be true for a long time for some special families of trees, including caterpillars. So in this video, we're not going to prove the full conjecture. We're going to prove a weaker upper bound. We're going to show that the Turan extremal function of n comma t is less than or equal to n times k minus 1 for every tree T of order k plus 1. And we'll also prove the conjecture when the tree is a path. So we won't prove it for caterpillars, but we'll at least prove it for paths. So let's see how we're going to prove the general upper bound on trees. This upper bound of n times k minus 1 for trees T of order k plus 1. So we're going to use this claim that we made in one of the earlier videos, the video on graph terminology. When we were discussing degeneracy, we made this claim about the degeneracy in terms of the number of edges and the number of vertices. So the claim is that if a graph has m edges and order n, then its degeneracy is at least m over n. Another way we can say that is if you have a graph with m edges and order n, it must have some subgraph where the minimum degree is at least m over n. That's the version of the claim that we're going to use here. So in order to prove this upper bound of Ex of nt is less than or equal to n times k minus 1, we'll take the right side of that bound, so the right side being this n times k minus 1, and we'll add 1 to it to get k minus 1 times n plus 1. And we're going to try to show that if you have a graph of order n with k minus 1 times n plus 1 edges, then it must contain every tree T of order k plus 1. And we're going to use the fact that this claim is true. So if we have a graph with at least k minus 1 times n plus 1 edges, then we can say that it has a subgraph with the minimum degree at least k minus 1 times n plus 1, all divided by n. When we divide that by n, we get a number that is strictly greater than k minus 1. So we can say that this subgraph h of g has minimum degree that's strictly greater than k minus 1. Since the minimum degree has to be an integer, it means the minimum degree is at least k. So what we're going to do to prove this bound is we're going to use what we just got from the claim, and we're going to combine that with induction. We're going to prove, using induction on D, that every graph H with minimum degree at least D must contain every tree of order D plus 1. And then note that if we have that claim true that we're about to prove by induction, then we can say that this graph G that has some subgraph H of minimum degree at least K, it must contain all trees T of order K plus 1. So this claim that we're going to prove by induction will give us exactly what we want. So let's see how we can prove this claim. If we're going to induct on D and show that every graph of minimum degree at least D contains every tree of order D plus 1, then we need to start with the base case. Our base case will just be D equals 1. And we can see that trees of order D plus 1 when D equals 1 are just trees of order 2. There's only one tree of order 2. It's the tree that has 2 vertices and an edge between them. And we see that every graph of minimum degree at least D, where D equals 1, so if it has minimum degree at least 1, that means that all of the vertices must have a neighbor. So if D equals 1, that implies min degree is greater than or equal to 1, which implies that there is a copy of P2, and P2 is the only tree of order 2. So we get the base case. Now for the inductive step. We will suppose that every graph of minimum degree at least D contains every tree of order D plus 1, and we'll use that to prove the next step of the induction. We're going to prove that every graph H with minimum degree at least D plus 1 contains every tree of order D plus 2. So we'll fix a tree and we'll fix one of these graphs H with minimum degree at least D plus 1. So we'll say T is a tree of order D plus 2. And H will be the graph with minimum degree at least D plus 1. And we want to prove that H contains T. So we'll look at T. So we can draw a picture, an example of some tree. So we can say, here's our tree T. So there's our tree T. And every tree we know has some leaf. So we'll say there's our leaf and we'll name it V. Now a leaf is a vertex of degree 1. So since it has degree 1, it has exactly one neighbor in T. And we'll name that neighbor W. So this will be W right here. And we look at a smaller tree that we get by cutting V out of T. So this smaller tree right here is T prime. And the whole thing is T. So we have the whole tree is T, the leaf is V. There could be multiple leaves. We just pick one of them as V. The neighbor of V is W, and the tree obtained by cutting V out of T is just T prime. Now we can use the inductive hypothesis here. We can see that H is a graph with minimum degree at least D plus 1. And T prime right here has order equal to the order of T minus 1. T had order D plus 2, so T prime has order D plus 1. Now, what was our inductive hypothesis? Our inductive hypothesis was that every graph of minimum degree, at least D, contains every tree of order D plus 1. H right here is a graph with minimum degree at least D plus 1. So not only does it have minimum degree at least D, but it has even more than that. It has minimum degree at least D plus 1. So using our inductive hypothesis, we can say that H must contain every tree of order D plus 1, which includes T prime. So we got H contains T prime. Then we look at the copy of T prime in H. So like this copy right here, we'll just say that that's an H. And we consider the neighbors of the vertex which represents W in H. So we'll say that that vertex, we'll give it a name. We'll say the vertex, here's an arrow. Its real name is U in H. And we're viewing this copy of T prime in H. So U in H, we look at the neighbors of U in the copy of T. And we see that, or the copy of T prime, copy of T prime. So we don't know if we have a copy of T yet in H. That's what we're trying to prove. So we look at the neighbors of U in the copy of T prime. We see again that T prime right here, it has order D plus 1. So any vertex in T prime has at most D neighbors in T prime, where D is equal to the number of vertices in T prime minus 1. So any vertex in a graph of order X has at most X minus 1 neighbors in the graph, the number of vertices minus 1. All of the vertices except for itself. So we see that this vertex U in H, which represents W in the copy of T prime, has the most D neighbors in the copy of T prime. On the other hand, H right here, it's a graph with minimum degree at least D plus 1. That means that the vertex U right here, let's give it a little arrow there, it has degree of U is greater than or equal to D plus 1. So we know that at most D of the neighbors of U are in the copy of T prime, but U has degree at least D plus 1. So U has some neighbor in H that is outside of the copy of T prime. And that neighbor, that extra neighbor, we will say that that neighbor is V. So we make a copy of T by taking the neighbor of U that is outside of the copy of T prime and adding that neighbor to our copy of T prime. And that forms a copy of T. And so we just found a copy of T in H using the fact that H has minimum degree at least D plus 1, but the vertex U in this copy of T prime has the most D neighbors in the copy of T prime. So it has at least one neighbor in H outside of the copy of T prime that can be used to complete the copy of T from the copy of T prime. And that completes our induction. So we were trying to prove that every graph of minimum degree at least d contains every tree of order d plus 1. And we just finished the inductive step, so the proof is complete. Now that we looked at the upper bound, it makes sense to look at a lower bound for the Turan extremal functions of trees of order k plus 1. We've actually looked at this lower bound already for some other families of graphs, but it has the same construction. And it's actually a very general lower bound that holds for all connected graphs of order k plus 1. So the lower bound is ex of nh is greater than or equal to k minus 1 times n over 2 for all n divisible by k, as long as h is a connected graph of order k plus 1. How do we get this lower bound? Well, we can just take a disjoint union of k cliques. So a bunch of cliques, a bunch of complete graphs of order k. And we don't have any edges between these cliques. And so we see that within each clique, it's impossible to have a copy of H because H has order k plus 1. It has too many vertices. And any copy of H, since H is connected, would have to be contained in a single connected component of this graph. So we can see that that graph must avoid H. It is H-free. And if we multiply n divided by k times k choose 2, then we get exactly what we see on the right side of that bound, the k minus 1 times n over 2. So that picture we just saw was a disjoint union of k cliques. And we can see that in the special case when the connected graph H is a tree, then of course we still get this bound. So we can say that the extremal function of n comma t is greater than or equal to k minus 1 times n over 2 for all trees t of order k plus 1, assuming n is divisible by k. And this bound is sharp. We've already seen it's sharp. So we saw that it's sharp for the star. So the star we know is actually equal. It's equal to k minus 1 times n over 2. Its Turan extremal function is equal to that for n divisible by k. Also, this is known to be tight for caterpillars. So caterpillars, the conjecture that we saw, the conjectured upper bound, was known for a long time to be true. And in fact, we know now, since the conjecture is proved, that this lower bound is sharp for any tree T of order k plus 1 as long as n is sufficiently large. But in this video, we're not going to prove that in full generality. We're not going to even prove it for the caterpillars. We're just going to prove it for paths. And it has a pretty nice short proof for paths. Here's a problem, though, for you to think about before we prove this result for paths. So prove that if G is a connected graph and G has minimum degree D, then G has a path of order at least the minimum of n and 2D plus 1, where n, as usual, is the order of G. So now we're going to prove that the Turan extremal function of the path of order k plus 1 is at most k minus 1 times n over 2. And we're going to prove this by induction on n. So our base case, we can just take our base case to be n less than or equal to k. And we can see that it's clearly true for these values of n. Why is it clearly true there? Let's look at that for a second. So the claim is that if n is less than or equal to k, then the extremal function of n comma p sub k plus 1 is less than or equal to k minus 1 times n over 2? Well, we can see since a graph of order n has at most n choose 2 edges, then ex of n comma p sub k plus 1 is less than or equal to n choose 2, which equals n times n minus 1 over 2. And since n is less than or equal to k, then we have n minus 1 is less than or equal to k minus 1. And that gives us n times n minus 1 over 2 is less than or equal to k minus 1 times n over 2. So this is how we got the base case. And then the inductive step. We're going to have this inductive hypothesis. Since we're inducting on n, our inductive hypothesis is that the extremal function of n minus 1 comma p sub k plus 1 is less than or equal to k minus 1 times n minus 1 instead of n over 2. And we're going to use the fact that we saw in that problem on the last slide. So if we have a connected graph G of order n with minimum degree d, then G must have a path of order at least the minimum of the order of G and 2d plus 1. So now we're going to try to prove the inductive step. We will let G be a p sub k plus 1 free graph of order n. In other words, G has no subgraph which is isomorphic to the path of order k plus 1. Now, without loss of generality, we can assume that G is connected. If it's disconnected, then we'll just apply the following proof to each connected component of G. Suppose that n is greater than k. Now, we can assume this because we've already covered the case, which was our base case, where n is less than or equal to k. So since we already covered n less than or equal to k in the second bullet, that's why here we're supposing that n is greater than k. Now, since n is greater than k, we can see that G is not only free of the p sub k plus 1, it also has to be free of complete graphs of order k. Why is this? Well, let's say that G had some complete graph of order k right here, and G has order n. So we know that the order of G is greater than k because n is greater than k. So that tells us that there must be some vertex outside of the complete graph k sub k in G. And since G is connected, there must be some vertex outside of this copy of k sub k in G that is connected to that copy by a single edge. And we know that k sub k contains p sub k. So we can take a p sub k in this k sub k that ends at this vertex, which is connected to this vertex out here by an edge, and we turn that p sub k into a p sub k plus 1. And note that in the k sub k, we can choose any permutation of the vertices to form our p sub k because all of the vertices are connected to each other. So we see that G is both free of cliques of size k and paths of order k plus 1. Now, we can use that claim that was in the problem on the previous slide, if G had minimum degree at least k over 2, then by that claim, G would have a path of length at least either n or 2 times k over 2 plus 1. So the length would be at least the minimum of n and 2 times k over 2 plus 1. And this is going to be greater than or equal to k plus 1. Why is that? Well, n is strictly greater than k, and 2 times k over 2 plus 1 equals k plus 1. So we see that if G had minimum degree at least k over 2, then we would find a path of length at least k plus 1 in G. That would give us a contradiction. So G must have minimum degree at most k over 2 minus 1/2. So we can assume that G has minimum degree at most k minus 1 over 2. And what we can do is, since G has minimum degree at most k minus 1 over 2, that means there's some vertex in G that has degree at most k minus 1 over 2. So we can remove that vertex from G, and by inductive hypothesis, the remaining graph has at most k minus 1 times n minus 1 over 2 edges. And that's because the remaining graph has order at most n minus 1, and the inductive hypothesis is in the third bullet. So we remove the vertex of degree at most k minus 1 over 2, leaving ourselves with a graph with at most k minus 1 times n minus 1 over 2 edges by inductive hypothesis. That tells us that the number of edges in our original graph, the G graph, the number of edges was at most k minus 1 over 2 for the degree of the vertex that we removed, plus k minus 1 times n minus 1 over 2, which is the number of edges in the graph that we obtained by removing that vertex. And when we add those two together, we get exactly what we were looking for, the k minus 1 times n over 2. So that brings us almost to the end of the video. All that's left is a problem for you to think about. Suppose that H is obtained from the complete bipartite graph k sub 2 comma 2 by adding 2 leaves to one of the vertices in the k sub 2 comma 2. So notice that the graph k sub 2 comma 2 is symmetric. All of the vertices have the exact same neighborhood relative to each other. So from the point of view of any vertex, the graph looks the same. So if we add 2 leaves to any vertex, the graph we obtain is going to be isomorphic to the graph obtained by adding 2 leaves to any other vertex. So it doesn't matter which vertex you add the leaves to, is what I'm saying. So if you suppose that H is obtained from k sub 2, 2 by adding 2 leaves to one of the vertices in the case of 2, 2, prove or disprove that the Turan extremal function of n comma h is big O of n to the 1.5. And this is the same order as the upper bound that we proved on the Turan extremal function of n comma k sub 2 comma 2. So the goal is to prove or disprove that adding those 2 extra leaves does not change the upper bound that we got on the Turan extremal function, except by, at most, a constant factor. Well, that brings us now to the end of the video. Thanks for watching.